Good day everyone. In this video, I'm going to define ethers. And after that, I will give you an example of ethers and I will teach you how to name the following compound. I will be discussing also the properties of ether so that you will understand. So, ethers are a class of organic compound that mostly contains an ether group wherein the oxygen bonded to two alkyl or aryl group. The word ether has been derived from the Latin word ether, which means to ignite. So let's go on to the example of ether. Number 1, methoxymethane or dimethyl ether, isopropoxypropane or diisopropyl ether, phenoxybenzene, diphenyl ether, ethoxyethane or diethyl ether. There are a lots of example of ethers, but I only give 4 examples. You can search to the internet for more example. In naming the ether, there are 3 rules. Rule number 1, always select the longest carbon chain as the base chain and give the base name. 2, change the name of the other hydrocarbon group ends with Y and L. Change to oxy. For example, methyl becomes methoxy and ethyl becomes an ethoxy group. Number 3, alkylene name is placed with a locator number in front of the base chain name. For example, the structural formula of 1-ethoxy and 2-methylpropane. So last of my assigned topic is physical properties of ether. A net dipole moment exists in an ether molecule. This is explained by the polarity of carbon-oxygen bonds. Ethers have a boiling point similar to that of alkenes, in contrast to alcohol with comparable molecular masses. It is considerably lower, and despite the carbon atom band's polarity, this is the case. So, ether miscibility with water is similar to alcohol miscibility, and water and ether molecule mix well. This is explained also by the fact that ether's oxygen atom may create hydrogen bonds with a water molecule, just like alcohol can. I think that would be all my topic, and thank you.
What's up guys, this is Aimee Simini and welcome to my video. So, I want to talk about the classification of ethers, the symmetrical ethers and unsymmetrical ethers. So, what is symmetrical ethers? Symmetrical ethers are those ethers where two identical groups are attached to the oxygen atom, or when the two alkyl groups are identical or same number of groups on both sides of oxygen. Like for example, of symmetrical ethers, they are same both sides of the oxygen. So, what is symmetrical ethers? Symmetrical ethers are those two different groups are attached to the oxygen atom. So this is an example of asymmetrical ethers. Different number of groups on both sides of oxygen. This is an example of asymmetrical ethers. Or like this one. This is an example of asymmetrical ethers. And this is the example of symmetrical ethers. They are same both sides of the oxygen. The asymmetrical ethers are different number of groups of the both side. This is the example of asymmetrical ethers. Different number of groups on both sides of oxygen. So, that's all. I hope you enjoyed this video. Thank you for watching. Stay safe and may God bless us all.
In preparation of ethers, ethers can be prepared or synthesized in a number of ways. The most common industrial method for preparing ethers is dehydration of alcohol. Alcohol dehydrates in the presence of protic acid, such as sulfuric acid, to form different types of ethers and alkenes. For instance, dehydration of ethanol at 413 K result in ethane, while dehydration at 113 K result in ethoxyethane when sulfuric acid is present. In Williamson synthesis, the most used technique for making ethers is the Williamson. A methyl alkoxide displaces a halide ion from an alkyl halide in an S sub N and 2 reaction, which is how it happens in alcohol and a potent base such as sodium hydride react to form the alkoxide ion.
Alkyl halide with dry silver oxide. When alkyl halide is treated with dry silver oxide, ether is produced. Ether chemical reactions. Ethers are less reactive functional group out of them. Bases, oxidizing agents, and reducing agents don't affect ether bonds very much. Ethers, on the other hand, experience cleavage through interactions with acids. These are the most common chemical reactions that ethers undergo. Cleavage of CO bonds in ethers, concentrated acids, high temperatures, and abundance of hydrogen halide cause the cleavage of CO bonds in ether. For instance, when dialkyl ether reactions, the result is initially an alkyl halide and alcohol. This alcohol and halide subsequently react to produce a second mole of alkyl halide and water. The oxygen atom in ether is known to be basic, just as oxygen atom in alcohol. A protonated ether is the result of the initial reactions between ether and halide. The CO bond is broken by the halide ions nucleophilic attack on this protonated ether. Formation of peroxides. Ether will form a peroxide linkage when it is exposed to air in the presence of sunlight of UV light.
Let us now move on the electrophilic substitution reactions in the case of aromatic ethers. We saw that in the case of ethers, oxygen has lone pair of electrons. Now, because it has lone pair of electrons, we know that it will be happy to share its lone pair of electrons on the benzene ring. We see over here at alkoxy group is releasing electrons at ortho and para positions. And when it releasing electrons at ortho and para positions, what will happen? An electrophile E positive, they like to come and attach itself at any of three positions. OR group is first of all ortho and para directing, and it is releasing electrons into the benzene ring. It is ring activating as well. Some of the different types of electrophilic substitution reactions include halogenation. Halogenation alkyl groups undergo a substitution reaction with halides such as chlorine and bromine. This reaction yields halogenated ether in the absence of sunlight. So we have here an example. Anisole undergoes bromination with bromine in ethanoic acid even in the absence of iron bromide catalyst. This productive Cowan system is p-bromoanisole minor product, and this one is the ortho-bromoanisole minor product. Now let us move on to the next reaction, nitration of anisole, means replacement by NO2 positive group. Whenever anisole is nitrated with a mixture of concentrated nitric or HNO3 and sulfuric H2SO4 acids. So our ortho is 2-nitroanisole minor and our para is 4-nitroanisole major product. Last is Friedel-Crafts reaction. These are a couple of reactions created by Charles Friedel and James Crafts in 1877 to attach substituents to aromatic rings. These reactions are of two types. First is Friedel-Crafts alkylation reaction, replacement by an alkyl group. We have here an example of alkylation. Anisole plus CH2Cl in the presence of anhydrous AlCl2 and CS2. Our ortho is 2-methoxytoluene minor product and our para is 4-methoxytoluene major product. The second reactions created by Charles Friedel and James Crafts is acylation. This reaction involves the acylation of anisole with an acyl chloride in the presence of anhydrous aluminum chloride as a catalyst. So our ortho is 2-methoxyacetopenon minor product and our para is 4-methoxyacetopenon major product. To be more specific, in each of these reactions, the ortho and para positions of the alkyl and acyl groups are introduced via reaction with an alkyl halide and acyl halide respectively in the presence of anhydrous aluminum chloride.